Welcome back everyone to Data Science for Everyone. Today we're going to be looking at weighted least squares with stats models. So let's get started. So let's go in and get some basic imports stated up, and then we'll get started with everything else. So import numpy as np. We're going to import scipy from scipy. From scipy, let's import in our stats. Import statsmodels.api as sm. Also import matplotlib.pyplot as plt. We also want in here as well from statsmodels.sandbox.regression. Import pred standard deviation. So import WLS prediction standard deviation. Oh, and we also need a couple more in here. Sorry. We'll do from statsmodels.io lib.table. Import here simple table and default text format. And then we also want to do mp.random.seed here, and we'll do 42. And then we'll also do in here matplotlib inline. Import, port, there we go. Stats models. There we go. All right, so first things first, let's go on and give us some titles in here. So we're going to do our weighted least squares estimation. Okay, and we're going to also create up some artificial data. Let's just do fake data. Fake data here with heteroscedasticity of two groups. And so we're going to have, actually, you know what, let me go on and actually put in, we're also going to have a couple assumptions. Okay, so one here is misspecification. Okay, so the true model will be quadratic. Okay, the estimate though is linear. All right. The next thing we want to do is there's going to be independent noise. And again, we're making fake data here in a second, so just make sure to take that into account, okay? So I'm just wanting to make sure that everything's kind of clear. So we want independent noise here, or error. We also are going to want in here two groups, okay, for error variance. Okay, low and high level, high variance groups. Okay, so those are our three. Our three assumptions there. Let me give it a little bit more space. There we go. So once those are kind of there, so then we can actually go on and make our sample data. So our in sample is going to be 50. We want x is equal to our line space, 0 to 20 to our in sample. Capital X is going to be np dot column stack here, and we want x such that x minus 5 squared. X is equal to sm dot add constant of x. Beta is equal to 0.5 minus 0.01. Sigma is going to be 0.5. W in this instance, let's do np.ones of in sample. And then W is going to be in sample multiplied by 6 integer division 10, continue on through, is equal to 3. Y true is going to be what? np dot x and beta. Error np dot random dot normal, size is in sample, and then y is going to be equal to y true plus sigma multiplied by w multiplied by e. X is equal to, that's cap x, is equal to cap x such that 0, 1. All right. So this is our fake data here. I know that it's a little bit, a lot of math in there, but this is going to just show us it's something, and everything's going to be nice and controlled for us, okay? So that we can kind of show you what's going on. Now, so let's kind of go and give us a little bit of notes here. So here the weighted least squares is going to be knowing the true variance, okay, ratio of the heteroscedasticity. Okay, so in this example, W is going to be our standard deviation. Okay, and our weighted least squares requires that the weights are going to be proportional to the inverse of the error variance. Okay, so let's do this. Mod weighted least squares is equal to sm dot weighted least squares. Here, y, x are weights, is equal to, again, the inverse, okay, squared. Oh, whoops. Now let's do our results for our weighted least squares here. Will be mod WLS dot fit. Again, we could have done those in one line. We didn't have to. Our results dot results for our weighted least squares dot summary. Okay, and we see our squares doing okay. Well, we have our Hark-Bara, we have all of the things that we've kind of talked about, our skew, our kurtosis, etc. Now let's go on and actually compare this out. Again, we always want to have some nice comparison, okay? So what if we compared it directly to a basic OLS model? Okay, that's the next part that we want to kind of compare with. Let me give us a little bit more space here. And so we'll be able to compare them, again, once we have this, we want something to compare to. So let's do it side by side. So OLS versus weighted least squares. So here, let's say our results for our OLS is going to be sm.ols, and again we want y, we want x dot fit, and we'll go on and do everything in one. And then you know what? Let's do print residuals of OLS dot params versus our print results WLS dot params. So we can compare the two. Now, there's not a terrible lot of difference here. So let's maybe go a little bit deeper and let's actually compare the standard errors to heteroscedasticity corrected for our OLS standard errors. Okay, so I'll put notes here. Compare OLS standard error to heteroscedasticity corrected OLS standard errors. So standard error is equal to mp.vstack. And we want our, what do we want in here? We want the BSE, again, because we're checking the errors. We want in here our results OLS with the same thing. Then we want in here our residuals, results OLS dot HC0 underscore SE. There's supposed to be another one there. What else? Resed OLS dot HC1 underscore SE. And then what else? Not old. OLS. We also want in here res OLS.HC2 SE, and then res OLS.HC3 underscore SE. And then let's do SE is equal to NP dot round SE to 4. Call names, we want x1, and we want the constant. Then we have our row names, and we want this to be weighted least squares, our OLS, OLS 8 HC0, and I'm gonna copy that because we're gonna H1, H2, H3. And then let's do our table. Is our simple table, our SE, our column names, our row names, our text format here is going to be the default text format. And let's go on and print tab. All right, and so here we can actually go on and compare these, and we can kind of see that, again, there's this OLS here definitely has, these two are definitely different, but then as you can see here, as we add in the adjustments, everything seems to be getting a little bit closer to one another, but never quite as the same. Now let's go on and do a bit of a prediction interval, and then we'll also go on and plot this out so that we can kind of see get a nice visualization of how things are going to go. So first off, let's go on and do our covariance parameters here. So res OLS dot covariance parameters. We'll do our prediction variable here is going to be our res OLS dot SME MSE residuals plus here x multiplied by x multiplied by MP dot product of our and this needs, I want this to be our covariance for beta, covariance beta x, the inverse there, and the transpose, sorry, not the inverse, sum of 1. Prediction standards, MP dot square root, prediction of var, and then we also want in here TPPF is equal to stats.t.ppf 0.75 results OLS of the data frame residuals. Whoops, what did I, square root All right, and so let's actually go on and draw a comparison between both of the models, the weighted least squares and OLS. So here, P prediction standards, IV1, IV mu is equal to our predictions standard res WLS. So we do fig. Axis is equal to PLT dot subplots fig size. Let's do 10 by 10. We also want our axis plot here X, Y, O. So to make nice dots, a label is going to be the actual data. Then our axis again dot plot X, Y, true. Will be blue dash line. Label is true. Axis dot plot. Oh, and let me put in some labels here. This is definitely going to be the OLS one here. And let me give a couple more, a little more space here. I think this is kind of getting a little hard to read for you guys. So let me put that a little bit bigger. All right, so OLS X, resid of the OLS, results for the OLS. Dot fitted values. We want this to be red dashed line. Here, the IV, U, OLS. So we want the actual, we want the upper and the lower. Label here will be OLS. Whoops. It doesn't need a label. And then actually I think I need to go back up and maybe make these real quick. Yeah, I didn't actually go through and make those. So let's do our prediction OLS. We want the IV L OLS. We want the IV mu OLS is equal to, and here are again our prediction of our results of the OLS. There we go. Now we actually have them. All right, so we have our reds. All right, so our OLS model. Now we need our weighted least squares model. And so we want X with our result of our WLS model dot fitted values. Here we want them to be green. And I want it with a dot. What else do we want? Let's do what? Green. This one will have the label of weighted least squares, x IVU. Oops, I did not mean to do that. There we go. I don't want to type in Chinese right now. Legend, let's put this at best. Oh, what are we missing here? Subplots. There we go. All right, and so here we can actually see we have our true data, we have our the true line here, we have our actual data, we have our weighted least squares, and then we have our ordinary least squares. So I would definitely believe that the weighted least squares are definitely better, because you can see here that it's taking care of these outliers on the side, and it's not quite catching that one, but it's actually being at least closer, okay, to those outliers, where the linear one just kind of almost blatantly ignores them and kind of cuts them off. Here you can see. So if you guys like this, please comment, subscribe, and hit that like button, and I will see you guys next time. Bye-bye.